So, good morning everybody, and welcome to day number 3. Again, a long morning for you. I guess I'll try to keep you awake. I would like to start with a short reminder of most important aspects we have discussed yesterday in terms of gas phase thermometry. So we have seen that we have different possibilities to measure temperatures, and we only have so far discussed the first one, where we take advantage of the Boltzmann distribution. So this method number 1 is this distribution given by the following expression, where you have, for the case of rotational lines that are the most sensitive ones with respect to temperature, rotational states I should better say, which are classified by their rotational quantum number, J, in the following way. So you have the Boltzmann fraction, which is the part of those molecules which are in a specific quantum state defined by the rotation quantum number J over all of these molecules being in the sample, is given by the degeneracy factor, that is the number of states that have the same energy, and that came to us here without any derivation, so you have at this stage simply to accept that. We have then the expression where we have here in this argument of this exponential function the rotational energy given by the state J over the Boltzmann constant and the absolute temperature. And this is over the partition function, which is the sum over all possible states J, which are well given by the same expression, 2J plus 1 times the exponential function of the negative rotational energy over kT. And I will not repeat in detail, or I can do that, the energy that can be calculated for the rotational substages is the following. In wave numbers, you have here the rotational constant that depends on the actual vibrational state V. It depends on where the substructure is looked at. Is it V equals 0? Is it V equal 1? And so on. Times the rotational quantum number times the rotational quantum number J plus 1. That is the rigid rotator. That is, of course, not true. A rigid rotator would not allow for higher rotation speeds, that the molecule is bended. That's why we have here a correction that is as well dependent on the vibrational quantum number, and to account for the fact that this is a correction that needs to be more and more for higher rotational speeds, where more and more the molecule is bended and the distance between the two atoms is increasing. That's why we have here this expression in this model where we have the same expression but squared. Yeah? Instead of J, we have J squared, J plus 1, J plus 1 squared. With that, given for a molecule, you will find the B and D values. You can calculate the energy in this rotation, and then by that you can calculate the Boltzmann fraction. For example, I give you here maybe for 2 temperatures to illustrate the basic idea. If you plot here the Boltzmann fraction Nj over N over the rotational quantum number J, which is discrete, yeah, it's only allowed for values 0, 1, 2, 3, 4, 5, and so on, maybe up to 10 here. Then we can maybe for a low temperature do find a certain distribution. These sticks devote to the scalar values you would find for that molecule that we're looking at, for example CO or something like that. And then for low temperatures, maybe you have a peak value for J equals 3, and then because of the exponential character of this distribution function, then this distribution decays rather fastly. And so if you take here the envelope, that gives you the direct impression or expression for a certain temperature T1. If you now have another temperature, and maybe I take here a different color, where, oops, you do have, let's say, a higher temperature, then the whole distribution function shifts. You have a lower distribution at lower values, but that changes such that higher values are now more heavily populated, and the distribution goes over to higher values, which are still detectable, and you will find a different envelope giving rise due to these higher temperatures. And the basic idea in gas thermometry based on this Boltzmann distribution is either to monitor the full spectrum. Yeah, each of these lines can be then found in the spectrum, for example, in laser-induced fluorescence or in cars that we discussed. And of course, you can do as well a different approach when you just take, let's say, 2 lines of them and take the ratio of that. Although, of course, it's obvious that if you do it only with 2 lines, then you're less precise, because each transition, each measurement of transition and the line strength will have a certain noise. And if you divide then by ratioing 2 noisy values, you're less precise than if you measure the complete spectrum. But in principle, that's doable. And we discussed here the following techniques that are used in turbulent flames. One is laser-induced fluorescence. Or in short, LIF. And here the basic idea is that you are starting from a ground electronic state, you excite the first electronically excited state, and linked to that you have different J levels as well involved. So this is the resonant excitation of your transition by having here a certain frequency nu lambda of your laser, which must have the correct value such that if this is here the energy axis, this is the energy, that you fulfill this resonant condition where you have, let's say, if this state is E1 and this is E2, such that this resonance is given by this expression that your photon is absorbed and transfers its energy to the molecule. After that, the molecule, of course, in this excited state is not stable, and it might relax very fastly, maybe to a lower lying level, which does have a certain lifetime from which, for example, then fluorescence can take place at a frequency, in this case, redshifted at smaller values. And you would do that now for at least 2 transitions, such that you would have in 2-line thermometry two lasers, 2 detectors. They are fired sequentially to each other, such that the radiation, the fluorescent radiation, is not interfering. And then you would get something like a ratio from these 2 fluorescence intensities, maybe denoting that here as intensity of fluorescence excitation of the 1 rotation level number 1, and divide that here by the fluorescence number 2. But here we have as well the involvement of eigenstates from which the fluorescence takes place. They have a certain lifetime, and you have collisional quenching. And this quenching gives rise to a certain lifetime, which is state dependent, quantum state dependent, and of course dependent on the surrounding, the colliding molecules, the pressure, and the temperature itself, because that changes the collision rate. And in case that the lifetimes are different between these 2 involved states from which fluorescence takes place, if they are not identical, then this expression is not accurate, not really true, because you have involved in this ratio as well, the ratio of the total lifetimes. And if you refer back to the notes you have, then you will find the expression in detail and find that these lifetimes actually need to be, when accurate, need to be identical, and that is not given, of course, in all cases. You might accept a certain inaccuracy if they differ only by a couple of %, but very often that is as well not studied in detail. Yeah, so we do not know for too many molecules how they behave with regard to the lifetime when exposed to collisions with other molecules for different pressures and temperatures. Okay, that was the idea of having laser-induced fluorescence used for thermometry based with these restrictions and limited to 2 lines only, because for each excitation you need one laser and one detector synchronized to that laser collecting that fluorescence. Having 2 of them already is quite expensive, because you need tunable lasers to excite that transition of a small molecule we're talking about, like OH or NO or something like that. Of course, you could in principle do it with 3 or 4 lasers, but that is typically not affordable. Another approach is given by cars, where you then overcome this limitation of only looking for 2 lines. In cars, coherent anti-Stokes-Raman spectroscopy, you have a very different process. So and maybe I should give you the idea about the principal setup of such a system. You conventionally in rotational vibrational cars, you start with a frequency doubled neodymium-YAG laser, which emits at 532 nanometers. So that is maybe a system with something like 6 to 7 nanoseconds, and maybe in the order of 500 millijoule per pulse, to give you some numbers. And then you have a beam splitter, and with this beam splitter you take one part of that to pump a dye laser. A dye laser which provides you a broadband pulse at 607 nanometers for nitrogen cars. And the remaining of that pulse, which is at 532 nanometers, I should put here the units, is again split into 2 parts, such that you do have here now 2 pump beams. I think we have denoted them as omega 1. And then you bring in here your red broadband under the correct angle. You have here a lens, and then you focus these 3 beams to fulfill the phase matching condition as we discussed. And in this probe volume, maybe I should draw this a bit larger, so we make a magnification of what is happening here. So you have these beams, omega 1, and the other frequency as well, omega 1, but in 2 directions that are called the pump beams at 532 nanometers. And then the 607, which is spectrally broader, is intersecting here. And then we have here this wave mixing. It's called 4-wave mixing, where you now generate in a certain direction your radiation. I think that it was at 473 nanometers for nitrogen, if you excite with 532 and 607. And you again do have here a lens, where you then collect this 473. You kill all the other beams, you don't need them anymore, and you send them to a spectrometer. And in the spectrometer, the different row vibrational lines are split off, such that here you have then a CCD camera, and you can see here your spectrum, which I will show in a second again. And this spectrum then contains the different Boltzmann, or the Boltzmann distribution, which is then fitted. You take a theoretical spectrum, and in the end you have only one free parameter, which is the temperature, which you fit to the measured spectrum. And the process should be as well, once again, maybe marked what is actually happening. So I'm running out of space here. I have to create a new page. Sorry for that. So what you do in cars is that you start from one level. You have your 532 nanometer radiation, which is not resonant with any transition. Some people call this as well as a so-called virtual state. The lifetime is almost zero, such that in the context of cars, you then send in this second photon, which comes from the broadband laser, and thereby you coherently pump this vibrational level and rotation level involved. I don't draw the rotation levels. And then you have the next photon coming from the same laser, the same green laser. That's why I call it again omega 1. And then you create the cars photon, which is then, in the end, the signal containing the Boltzmann distribution. So due to cost reasons, you take these omega 1 photons, this one and this one, as 532 nanometers. In principle, of course, you could use as well two different lasers. If you have another laser in stock and you just want to use it, it doesn't matter. The only thing which is important, you should not hit any resonance. You should not pump any transition to a loud state. So these dotted lines are, as I said, called by some people virtual states. They do not exist. They are not allowed. The lifetime is close to zero. That's one thing. And the other thing I want to mention is that it's important that you hit the Raman resonance, meaning that the difference of the frequencies omega 1 minus omega 2 must be a Raman allowed transition. So this here, this separation, omega RS, is the separation between these two vibrational states and the rotation lines involved with that. Again, the rotation lines are so close to each other that I can't include them easily in this drawing. And then you have as frequency coming out of that process omega 4, I've called it here omega 4 for some reason. Omega 4, I think in the script it was omega 3, sorry for that, which is here 2 omega 1 minus omega 2. This is then the energy balance. That needs to be fulfilled. So once you have chosen omega 1, this 532 nanometers, as the wavelength from your frequency double Dirac laser, you're not free anymore. Then you have here, if you take nitrogen as the tracer molecule from which you deduce the temperature, then this frequency must correspond to the 607 nanometer, and then you get the car signal at a specific wavelength or frequency. And the second thing that was here new compared to the linear techniques that we discussed before, this is a nonlinear technique. Here you have to fulfill the phase matching. And we have seen that a photon not only carries energy, but it carries as well momentum. And the momentum of a photon is given by the wave vector k. It is proportional to that, and this is the reduced Planck's constant. And so whenever you create a photon like omega 2, and here in this denotation it's omega 4, whenever you create a photon, the momentum must come somewhere from. And whenever you destroy or absorb a photon, like these two omega 1 photons, then the momentum must go somewhere. And in the nonlinear spectroscopy, you must fulfill the momentum balance such that the wave vectors involved with that process, K1, and maybe it's not so smart to call that all the time omega 1 and here. I would actually prefer, when I do that here on the board, to call the pump photons omega 1 and omega 3, and then you might add that. Then it's easier to come up with this phase matching here. Then we should call that as well K3, because it has a different direction. It's the same frequency, the same wavelengths, but the direction is different. That's maybe better way calling that differently. And then these two photons are absorbed, and their energy is transferred in the first step here to the vibration, and then it's taking off from the vibration in such a way that you create here an additional Stokes photon, which is then here in our denotation K2. And then you create, that is what we're after, a photon K4 carrying the momentum K4 and the frequency omega 4. And this is in a certain direction. And because you shine in these three lasers, your signal carrying the information about the Boltzmann distribution has as well one distinct direction. It's a coherent beam. You can take your detector far from that. Yeah? You don't have to put your detector very close, like in the linear techniques, like in fluorescence, to collect as much as possible. Here, this is a real advantage. Think of a gas turbine, where you cannot place your detectors easily close to that because you have a high noise level, it's very hot and so on. Then you can place the detector maybe even next door. And so this is a very important feature that makes it so attractive as well for really harsh environment. And I would like you to remember that here you actively have to fulfill the momentum balance. Of course, in linear techniques, the momentum balance is as well fulfilled, but you don't have to care about it. The momentum is then taken by absorption from the molecule or by emission given from the molecule. Okay, there was a question, please.
Yeah, in practice, if you have a tunable laser to generate omega
2?
How do you do that? Because with the tunable lasers, they shift sometimes. So when you set up the experiment, how do you find the correct wavelength?
How to find the correct wavelengths. So you're talking about a home-built laser?
No, but I mean, I've worked with like tunable dye lasers.
Okay.
And it's not OH clip. And we have to usually find the OH line.
That's correct, yeah. So there are different options. So if you mistrust the reading on your commercial laser, which you maybe should, then the best way is if you're talking about tuning, so we are not about broadband cars, but scanning cars you're talking about, then you should have, the best possibility is to have a wave meter with which you have a fiber coupled, which is calibrated against a stabilized helium-neon laser often, where the accuracy of a wavelength reading is very good. That might be special because we're talking about quite a high price. You might have a spectrometer that is already in cars involved because you have to spectrally disperse that. Why not directly using the spectrometer and sending your omega 2 beam through that and look for the wavelength to have a good starting point. And then you start scanning. And if you don't hit a Raman resonance, because the population, maybe you're in a position where you have no resonance yet, then you wouldn't see anything. You scan further and further, and then it will appear. But of course, it will appear only if your pre-alignment is rather okay. Yeah? But we're talking not about, you don't have to be precise as, I don't know, half a wave number or so, because the band of nitrogens is rather broad. So you just have to be somewhere, look for a signal, maybe tune the wavelength to the strongest transition, if you go, for example, for nitrogen in air, and then you realign with your beams prior to the lens, the angle of these three beams, and optimize it, and then do your experiment. It's a broadband, you know, the way we do that is a broadband dye laser, the simplest version would be you tune your grading to 0 order, in the resonator you just have a mirror, and then you take a dye laser, or the dye solution, mix it such that the central frequency is at 607 nanometer, okay? That can be easily looked at with a relatively, with a simple spectrometer, such that you have the intensity at the right spot, and then you don't have to tune anything. Yeah, because all the frequencies and wavelengths you need for driving this Raman coherences are already inside that beam. Yeah? And so that is just then a question of the right mixture of dyes. You can do it even without a mixture. You can use one, but maybe then you're in an intensity which is not as high as it could be. But anyhow, you have to be careful with the intensities. It depends on the situation. You do not want to have here, let's say, too much pumping, because then the hot band will appear higher than it is naturally. Yeah, that can appear. Yeah, so for atmospheric flames, I don't have the numbers. Of course, it depends on the mode structure, on the lens system, and so on. But it's in the order of, let's say, 10 to 15 millijoules. This is in the order up to 10 millijoules that we presently take. If you would take 100 millijoules and 50 millijoules, by far too much. Okay. All right. And then, if everything runs well, again, these single-shot spectra. So these have been obtained in a combustion lab. It's not the best surrounding with a time resolution of a couple of nanoseconds. And you see here for low temperatures the transition from the vibrational ground state to the first vibration excited states, and because of the spectral dispersion, because of, no, this is wrong what I'm saying, because of the low temperature and of course the resolution you have, the underlying, let's say, handful or 15 rotational transitions are not really resolved. That is a problem in rotational vibrational cars. For low temperatures, it is not as precise as you wish or as it is for higher temperatures. For higher temperatures, here around 1000 K, you see here the different transitions. All these little spikes are due to rotational lines that are below this Raman transition. And here, the first hot band, this first hot band is due to the fact that you start here from V equal 1 and go to V equal 2. And for even higher temperatures, you see then the next hot band, and very nicely this rotational structure. And for nitrogen, we know the spectroscopy, the characteristics quite well, such that the spectrum can be modeled accurately. And if you have set in your model the transfer function of the spectrometer, the line width of the laser, and so on correctly, then the only remaining parameter in this fit is the temperature, and you tune the temperature to that point in the fitting routine such that the residuum shown here in blue is minimal. And then you can read these numbers here, and it really makes sense that we have here single-digit precision. Yeah? Because if you would write here or look for the spectrum with 2145 Kelvin, you would see differences in the residuum. Okay. If you now look for the precision, with this setup, you can reach something like, if you have the best instruments you can think of with a single mode YAG laser, you're at 2000 Kelvin, you can reach something like 20 to 30 Kelvin single shot precision. And that is not achievable easily by any other technique. And as I said, it's accurate because you trace it back to the Boltzmann distribution. There is no, in that sense, then no calibration required by principle. Yeah? Okay. I hope with this reminder is a bit more clear than yesterday. Do you have any questions about that? Yes?
What was the spatial resolution?
The spatial resolution. The spatial resolution is given by the overlap of these three beams. And what do you do if you want to have a higher resolution? Would you decrease or increase the angle between those beams?
Decrease the angle.
Decrease the angle. If you decrease the angle, let's have a look. There, I make it simplified now. Let's say they're in your focus like that. They have a certain extension, and you would have a small angle. Then you would have, in this direction here, a very long overlap. So it's worse. So this is the critical direction. If you have a very small angle over here, you might have something like 2 millimeters. If you increase it, of course, then you still have to consider the phase matching and so on. Increasing means a shorter working distance or larger length, and both might be limited. But the best you can maybe achieve here is something like 0.5 millimeter in this direction. This direction is given by the focal spot size, and we have seen a certain relation for that early on this week. That is dependent on the wavelengths, which you can't change. It's dependent on the focal length, which is given now, let's say. Then the only thing you can do is increasing the diameter of the beams at the lens, and you get a sharper focus. And to give you a number, 50 microns is maybe something you can achieve, 50 to 100 microns. So a bad direction with 0.5 millimeter or a millimeter, and a good direction, 1/10 of a millimeter. And that means in this direction, the smaller scales might not be resolved. You might have as well contributions from different temperatures inside that probe volume. And that will shoot up directly in the spectrum because then the spectrum cannot be fitted by a single temperature. You will see that in the fit. Okay. Yes?
Yesterday in the lecture, you just briefly mentioned femtosecond, picosecond cars.
Yes.
Could you go just into a little more depth about how they're different from the cars setup that you described, and what allows them to do 1D and 2D measurements?
I can include that in a lecture about flame-wall interaction. I can show their setup. Is that okay?
Yes.
So we postpone that for that. That is a setup from Sandia, from a colleague, Chris Cleaver, who did it with a femtosecond and a picosecond laser. And actually, we used that in a collaboration to measure temperature profiles perpendicular to a wall. And maybe that's a better opportunity then to explain that, because then I will make, I'm not sure whether it's included now, but it will make sure that it's included a setup. Okay? Good. Then we can proceed. As the next part, which will be not that comprehensive, we will see how you can use temperature-dependent absorption and emission lines for thermometry. This is done in connection with fluorescence spectroscopy. And for that, typically, tracers are added to the gas. And typical tracers are either hydrocarbons, like aromats, ketones, or aldehydes. And in some cases as well, people have used atoms, like indium atoms, that was brought to the mixture or to the gases by, for example, dissolving indium chloride in isooctane, spray the isooctane in an engine, then in the flame front, this indium chloride is decomposed and indium atoms are formed. But that is a very specific method. That's why I concentrate here on the more often used hydrocarbons as tracers. The good thing about that is you can choose your tracer, and as well linked to that its characteristics in terms of spectroscopy, dependent on what you want to measure. And that is, of course, something which is good if you have a certain control. But there are many cons. These molecules, aromats, ketones, and aldehydes, they are thermally, for temperatures exceeding something like 700 Kelvin, depending, of course, in detail on the tracer, they're thermally unstable, such they are decomposed for high temperatures. So that's why this kind of tracer live is primarily useful for gas mixtures that not yet have been reacted. So in the pre-reaction zone, in the mixing zone, for example, very popular in IC engines. Yeah? There's another con. Tracers may influence the properties of your fluid. Think of a laminar flame speed. Let's say you're after a gas engine where you burn CH4 with a certain flame speed, and you add a tracer by maybe 10%. That will change your laminar flame speed, and thereby as well the property of your combustion device. And as well, you have different densities, you have different viscosities, and thereby, in that sense, they're at least partly intrusive. And another drawback for at least some of these tracers is that some of them are not independent of the surrounding gas phase. And so if you want to use them for thermometry, there might be as well a cross-sensitivity. And this cross-sensitivity in most cases is due to quenching with molecular oxygen. And so we have to consider that for these different hydrocarbons. And of course, there exist many of them, and not all of them can be discussed over here. To give you an overview what people have used, very often ketones like acetone, or as well some people have used regularly 3-pentanone. In terms of aromats, toluene has been used as a tracer. That will be discussed in some more detail, as well as aldehydes like acetaldehyde, but of course here the list is not complete. And still the search for other traces, better traces with more quantum yield, meaning a higher probability to get a fluorescence photon out, are investigated. The problem very often, like for toluene, for example, is that they are prone not only they're not only temperature sensitive, but their signal, the fluorescence signal as well, will change with increasing oxygen contains or concentration. The fluorescence yield will decrease, because here these collisions with oxygen very often open up a pathway for relaxing the energy without emitting a fluorescence photon. Okay, so instead of going through these different options, I will do it differently, and in a classification show what principal pathways you have in this kind of tracer live. One option is that you have a tracer which is excited at two lines. You take two lasers, and in the absorption band, example will come, you excite the molecule to detect and use then a one-color detection. So independent on where the excitation takes place, maybe at lambda 1 and lambda 2, the fluorescence spectrum after the excitation is more or less the same, meaning that the detectors you're using are looking basically for the same spectral range. They use the same filters. And so in terms of the experimental setup, practically you need two lasers which are fired subsequently, maybe with a separation of 100 nanoseconds or so, to give fluorescence time to decay, and then do the next excitation. And synchronized to these two lasers, you have two cameras which are equipped with the same filters, looking for the identical spectral band. This is based on the fact that the temperature information is hidden in the absorption band, which is changing its shape, its absorption strength with temperature. It becomes clear with the example that follows the next transparency. The other possibility is that you use only a single laser. That has a lot of advantages, because it's not only cheaper, but as well you don't have to align two lasers exactly on top of each other, which can be problematic in practice. Okay, so we have one laser, but the emission spectrum will shift and change its shape with temperature. And then you can use a so-called two-color detection. You use two detectors equipped with different filters. They're looking for different parts in the spectrum, and thereby can monitor how the emission spectrum changes when the temperature is increasing or decreasing. And to visualize that a bit more, I have two examples showing that. The first is the two-line, one-color thermometry based on 3-pentanone over here, with some more information given in this review in this textbook over here. What you see is for the 3-pentanone molecule, the absorption over the wavelength. So most of these tracers we are talking about, specifically those hydrocarbon-based tracers, are absorbing in the UV. So you need a UV laser. Actually, for two-line thermometry, you need two UV lasers. Here it's shown for 3 wavelengths, 248. That is a wavelength you can achieve or extract from a excimer laser, krypton fluoride, 308 from a xenon chloride excimer laser, not so popular anymore. And 276 can be achieved by Raman shifting this wavelength. More common these days is maybe 266 nanometer, which is the 4th harmonic of a YAG laser, emitting its fundamental at 1064. The important aspect is you see now for different temperatures between 370 and 523 nanometer Kelvin how the spectrum is shifted. And now the basic and simple idea is you have one laser maybe at this part over here, and the other one maybe here. And then depending on the temperature, the absorption will change, and thereby as well the fluorescence intensity will change subsequently, such that the ratio of these fluorescence intensities is a function of a temperature. This is shown here. The function of a temperature is given as the ratio of the absorption cross sections for a given temperature. They are different for lambda 1 and lambda 2 if you probe them at 2 positions. And of course, this phi over here, this is a quantum yield, saying that the percentage of the molecules that are excited actually fluoresce and do not lose the energy by collisions. And so this is as well included in this ratio that is different for different excitation wavelengths, and as well is changing generally with the temperature. that can be calibrated. So you need a calibration. Yeah? You will have something like a cell or another useful device where you know the temperature, and then you can get this ratio by knowing the conditions and then do the experiments with unknown temperature and compare it or use the calibration for that. So that's one possibility. But you have to overlap these two lasers. You need two, if you do it two-dimensionally, you need two cameras which are synchronized to these two lasers, and thereby it is not an easy and not a cheap experiment. The other possibility, and I will go deeper into that at the end of this chapter, that's why I give you only here some basic idea, I come back to that, is toluene. That is a aromatic tracer that can be excited in the UV with a single wavelength, so a single line. But then you will see here, upon excitation, as well in the UV spectral range, you see here the different emission spectra normalized to 1 with a maxima. In reality, for higher temperatures, they will get smaller and smaller in the total intensity. With increasing temperature, these normalized spectra are red shifted. And if you now think, you take, or imagine you have now two detectors, they look at the same time upon this fluorescence, and one is looking for this spectral band and the other one for that. We call that blue and red channel. Then the ratio of these intensities of blue and red channel will change when the temperature is changing, because then the blue channel for higher temperatures will see a smaller intensity, whereas the red will see a larger one. And you optimize those filters to have then the ratio being dependent on the temperature to be very sensitive in the entire temperature range you were interested in. The application comes later where I show how you make use of that. The problem with toluene, as a side note, is it is very strongly dependent on the oxygen concentration. So if you perform these experiments in nitrogen, you have a huge signal, even if your excitation intensity is not as high. But if you operate with, I don't know, 10 to 20% oxygen content, due to the strong quenching, your signal can be decaying by a factor of, by 2 orders of magnitude. Yeah, that is really the drawback of this system here. Okay. Any questions about this principle, at least? Okay. Then we can go on and look for the last possibility to look for temperatures, which is based on measuring densities. Once you have the densities, using, in addition, an equation of state, most simple one is the ideal gas law. So the density in this context is simply given by by the number of molecules, and I mean now all molecules, not only a specific class, in a certain probe volume. So if you have a technique that allows to deduce this density, then you directly see with a known pressure, with the Boltzmann constant and this inverse density over here, you directly can deduce this quantity, this temperature. And now the question is how you can measure densities. And that brings me back to Rayleigh scattering. To remind you, Rayleigh scattering, different to absorption of fluorescence measurements, is like in cars, using a laser that is not resonant with any transition. So you're pumping the system into a state which doesn't exist. As I said earlier this morning, sometimes called virtual state, from which it returns directly if you don't do anything else, not a second beam like in cars. That's the only thing you shine in. It returns back to an allowed eigenstate, an existing eigenstate. And in Rayleigh scattering, it goes back to the state where it came from. So the initial equals the final state. That means that the scattered radiation, if we have here the frequency of your Rayleigh scattering, the omega 0, which is the laser frequency, is identical to the Rayleigh scattered light. And that brings me directly to a problem you might have. I will visualize that in a second in an image. The laser light might be scattered as well from a surface. So imagine you want to have measurement of your density very close to a surface. Then the laser probably hits the surface and of course scatters in all directions. And it scatters with the laser frequency. But if your Rayleigh scattering frequency is the same, you cannot easily distinguish them. So measuring close to surfaces, or as well in the presence of particles, make this technique very critical to handle, or even impossible. No time here to discuss some ways out, like filtered Rayleigh scattering, that provides at least a potential to solve and overcome this problem to a certain extent. So for the moment, it's just important to see what the process is doing, to understand this is here an elastic scattering processes of light from molecules. Yeah? Elastic because the frequency is not changed. And the basic physical view on that, a simplified view, is that you have a wave, electromagnetic wave, and we just look for the electric field component, and this electric field is interacting with the molecule, with the electrons and the nuclei, and what it is doing, it poses a force on that molecule, and the molecule starts to oscillate. This is a Hertz dipole, and the Hertz dipole oscillating is emitting radiation with its vibrational frequency. Yeah? So this oscillation frequency, and that is actually what is happening over here. So what we can do is a simple, or look at a simple setup. So you would need a laser. And here you really need a laser because the process is not so strong as in fluorescence measurements, for example. You need a pulse laser with, if you want to do a single thermometry with short time intervals, a pulse laser, let's say again a YAG laser, a Q-switched YAG laser with, let's say, a joule at 532 nanometers or so, and then you have this laser beam over here. You maybe focus that. Then you have a lens system to collect that, and you monitor that with a detector. Probably in front of the detector as well, you might have a filter, because if surrounding or light from your lab, for example, should be removed, then a filter is very helpful. And you will see that having shorter wavelengths is beneficial, but I come to that point in a second, because the Rayleigh cross-sections are getting higher if you have shorter wavelengths or higher frequencies in your laser. So a very simple setup. If you would do that here with a system, let's say if you have a pulse energy, just a side note, let's say of 1 joule, and let's say you have frequency double radiation from a YAG laser, 532 nanometers, and you would use a spherical lens and focus that directly in your flow. Any idea what would happen? Pardon me? A spark. No chance to do it like that. You can do it like that only if you would do a light sheet with a cylindrical lens. So in the case of a spherical lens with a joule with 5 nanoseconds or so, the intensity, the electrical field strength would be so high that you just distract the electrons from your molecules. And that is nothing else than a plasma, and we call that a spark. Of course, that needs to be avoided. If you want to couple in a high amount of energy, like 1 joule, and still want to have a spot size over here, you would have to stretch that pulse. Yeah, you have to make it longer to get down the intensity but keep the energy. It's in Rayleigh scattering, it's only the number of photons interacting. It's not like in cars where you want to have the photons in a short time to have a high intensity. Photons per time in that sense. Yeah. Here it's just the number of photons. And maybe we have some time later on when I discuss Raman spectroscopy to detail that a bit more, how you can stretch a pulse. But the principal setup is very easy. Okay, let's say you know the gas composition. Forget combustion for the moment, or you're in a region where combustion not yet has taken place, and where you know exactly what the gas composition is. That is the most simple case, where the local Rayleigh intensity is dependent on a Rayleigh cross-section that is given by the polarizability. Once again, the view I try to give to you. You have your time-dependent electromagnetic wave. And what it's doing, it is distorting the electrons from the nuclei. And this is called the polarizability, how easy you can pull the electrons back and forth. And different molecules do have different Rayleigh cross-sections because those electrons are stronger or less strong bounded to the nuclei. And if they're less strong bounded, they can be more easily moved, and that's why in that case this cross-section would be larger. It scales linearly with the laser intensity, and this is the important point, it is proportional to the density. Yeah? And the higher the density, the higher the pressure, for example, in a constant volume, then you would have here a higher Rayleigh intensity. Very important, because of the setup over here, that needs calibration. If you have a larger collection angle, you would have a higher signal. And this, for example, as well as the detection efficiency, filter losses, and so on, all of that is hidden in the calibration constant. It needs calibration, which is a large drawback against those techniques based on Boltzmann, which do not need that. So if you know the gas composition, then, as you will see in a second, you know the Rayleigh cross-section. Then you measure the laser intensity, and after a calibration, you can directly deduce the temperature, as I said, in connection with the equation of state. In this simple case here, assuming the ideal gas law. We have seen this formula already, where you need to know the pressure. In many applications, that's not a problem. You just need, because it's homogeneously distributed, you just need to measure that at one location with a piezoelectric or piezo-resistant transducer. And then I just resolve this equation here for N over V and put that in. And you see that you get the temperature if you have here done this calibration properly in a known mixture at known temperature. Okay, so in principle, you just have to then in the measurement after calibration take the laser intensity for each shot as well as the Rayleigh intensity. The Rayleigh cross-sections in a rather good model can be traced back to their index of refraction as given here. You see here N is the index of refraction of species I. This is Avogadro's constant, and lambda is the wavelength of the excitation, and that is an important relation. The cross-section scales with 1 over lambda to the 4th power. It's extremely nonlinear, meaning the shorter the wavelength, the higher the cross-section. And that means, when possible, use not a laser in the visible, use a laser in the UV. And you will need less energy, because that goes only linearly into the relation, but you will gain enormously from that inverse power dependency of this cross-section. Okay. I think that is relatively easy. Very often it's not like that, because in many cases the gas composition is not known. And then, although the same relation holds, the problem is this Rayleigh cross-section. This Rayleigh cross-section for an unknown mixture must be taken somewhere from. And so you need to have then an initial technique that allows you at least to estimate in a reasonable way the gas composition. And we will see that in chapter 7, I guess, in the gas phase concentration measurements, that Raman scattering, which is then applied simultaneously to Rayleigh, can solve that issue. That you then take the gas composition from Raman scattering, with which you then calculate, I'll explain that in a second, you will deduce the effective Rayleigh cross-section, from which you then, by measuring the laser intensity and the Rayleigh signal, deduce the density, and then again with the ideal gas law, for example, calculate the temperature. Because the problem is, as I already said, different molecules have different polarizabilities. And that means the cross-sections are different, such that in a gas mixture, we are not speaking about one cross-section, but we have an effective cross-section, which is the mole fraction weighted sum of the cross-sections of each species. Yeah? So xi is here the mole fraction of species I. This is multiplied with the cross-section of each species, and then you sum it up. And for example, take an example. If you would have air, and we just say we have maybe 80% nitrogen and 20% oxygen to make it easy, then you would have in air the content of O2 would be here 0.2. The mole fraction of N2 would be roughly 0.8. And the cross sections are different between these two species. If you go into a flame, you have as well CO2, water, and so on. And all these main species really contribute to that, and they have partly very, very different cross-sections. For example, the cross-section for methane, I forgot the exact number, but relative to nitrogen, it's nearly an order of magnitude. It's really different. If you don't know these composition, you will have here an unknown quantity, and then you cannot deduce this density. Okay. No questions about that? Then I will just start the discussion and then shift it to chapter number 7. That's why Rayleigh spectroscopy is done regularly, at least in few labs, simultaneously with Raman. And if you measure the Raman spectrum and do that measurement with a rather low dispersion, such that we can't resolve the rotation substructure, then you can get these gas compositions from this multi-scalar measurement, and we'll discuss that in much more detail, and then deduce the temperature in connection with a known gas composition from Raman by the Rayleigh part. And that is shown over here, at least the principle, as I said. Chapter 7 will detail that more. The idea is now that you have here in Raman, using the same laser as in Rayleigh, you excite as well to this virtual state, which is almost with a lifetime of 0. And then with a probability, let's say, of less than 1,000, you do not see returning to the ground state, where the initial is the final state, but as in the Cars process, but here only by excitation with one laser. This happens spontaneously. In Raman, Stokes Raman, it returns to a higher vibrational state, such that a species number 1 with a certain separation between these two vibrational states, this separation is different for other species, such that due to this different separation of allowed vibrational states, the scattered light denoted here by this arrow pointing downwards, this does have different frequencies, calculated by the laser frequency from which you subtract this Raman resonance. Yeah, the same here. And because these Raman resonances do have different values, the energy gap between them are different. You see here, as correspondingly in this view graph, the length of this arrow denoting the energy, the frequency of the scattered light is different. And that's why you can say a different species, the Raman scattered photons will have a different color. And this different color is then simply dispersed in a spectrometer before it's detected. And this will be discussed, as I said, in chapter 7 in more detail to give you some idea how such a spectrum from a flame might look like. You excite at 532 nanometers, somewhere here again. That's a laser providing cheap photons, and many of them. And then you see here the Raman allowed transitions, raw vibration Raman from CO2, O2, CO, N2, CH4, water vapor, hydrogen, and as well some interfering species like C2. That's always a problem if you go for rich or even slightly rich conditions, as well as you see a lot of noise. So the experiment done in a single shot, it's the red one. And here it was fitted, a theoretical spectrum was fitted with showing here in the green line, including as well a background. And then the idea is to be explained in more detail that you get access to the main species concentrations or mole or mass fractions, giving here. So the main species in a hydrocarbon flame, in a methane flame, are then the CO2, the O2, the CO, the N2, the methane, water, and hydrogen. And that is then the gas composition. And this gas composition goes into this formula. Then you have the effect of cross-section. And with that, you can then deduce the temperature. That is something I will explain later on. OK. Are there any questions about that principle? Yes, please.
In a couple different places, we've used the ideal gas equation.
Yes.
Does
the question is whether the ideal gas law holds. So for atmospheric conditions, it's okay. If you go for high pressures, where you have then molecule-molecule interactions, of course, then this equation of state is not valid anymore. As you, I guess, know, then you might have different choices, like the Peng-Robinson equation of state as one possibility out of many. The idea then is you have to account for these molecular interrelations. And but then you have to change your strategy with this different equation of state. Actually, I don't remember, at least from our community, any paper who was applying that, because the problem with it is whenever you have then conditions which force you to use a different equation of state, then you have an enclosure. And whenever you have an enclosure, you have stray light. And I would like to rewind back. I think I have shown that on Monday in our combustion chamber when we were sending through the laser for cars, how many reflections you get. And differentiate against these reflections will be difficult. With simple Rayleigh, it will not work. So people have developed so-called filtered Rayleigh scattering, but that brings us here in this introduction too far. There are at least ideas how to resolve that. Yes, please, Chris.
You mentioned that the Rayleigh scattering cross-section depends a lot on the laser frequency, very strong and non-linear.
Yes.
And so you could use a UV wavelength, and that would increase the signal. But doesn't seem to be so often actually done. Is that because in the combination with the detector?
The question is, when it's so beneficial in terms of the cross-section, why not using all the time UV radiation? I think, from my perspective, if money doesn't count, the main drawback is if you do it in the UV, you need a intensifier in front of your CCD or CMOS. And if you have an intensifier, it is so much harder to make quantitative measurements because of the noise. And these types, that is, I would say, the main reason. And for that, to make really precise measurements, it's better than to use visible light, and green is the most cheap one still, where the CCD, based on our CCD technology, has a high quantum efficiency in that range as well, and that's why I think that is the primary reason. Okay, if there are no further questions, I think it's already 1 hour ago. Strange. I think we make a break now, and we'll meet again here at 10:05, if that is okay. Thanks.